Hi, I Aziz welcome you to CoedMaster, and in this video I am going to talk about how numbers are represented and stored in memory. So let's get started. So before we begin our journey of bit manipulation and bitwise operators, let's first understand how numbers are represented and stored in memory. Why I am talking about numbers specifically? Because numbers are the fundamental unit of data. Let's look at on your keyboard. You find keys like numbers, alphabets, special characters. But internally, all these keys are associated with numbers only. For example, let's say the keys are 1, 2, 3. So these are the numeric keys, and this numeric key already has associated with numbers. If you have ABC, then each character is associated with a number. And if you see special character, it means the special character is also associated with numbers. So if you write numbers or a string or a special character, the internal representation is always associated with number. It means internally numbers are processed when you enter any string, special character or numbers. Clear? So that's why numbers are the fundamental units of data. Moving on. So now we have two types of numbers. One is positive numbers and one is negative numbers. In programming languages, we have data types to store numbers. For example, in Java, we have data type with name integers, and that integers is capable of storing negative numbers as well as positive numbers. So for now, just let's consider that we have only positive numbers, and then we will see how to store and represent positive numbers in memory. So for example, we have 2 and 1. Okay, so how 2 and 1 gets stored in the memory? Is it going to store as it is, or we have to convert it? Obviously we have to convert it, because computer do not understand what is 2 and 1. Computer only understand ones and zeros. So we have to convert the value of 2 and 1 into ones and zeros. Okay. So now the question is, how many bits we require to convert this number into binary, right? Because 1 and zeros are binaries, and we have seen in previous video that any data is represented in binary digits format, right? So how many bits are required? So let's say we are considering that we are using a system with 4 bits representation. Okay. So although in programming languages use 16 bits, 32 bits and 64 bits. But just for the ease of understanding, we are saying that we are only using 4 bits to represent any number. So when we convert from decimal to binary, then we get 0010, and this is going to be its binary representation. Okay, same with the number 1. So the binary representation of number 1 is going to be 0001. Okay, so this is how we represent 2 and 1 in binary format, and we store the same representation, binary representation, in memory also. Okay, so far so clear. Now think about that your computer is doing a lot of computation, right? Whatever operations you are performing, internally it is doing some kind of operations, and that operations are nothing but the arithmetic operations, right? So if we have positive numbers only, then how we perform arithmetic operations? So let's say I want to add 1 plus 2. So how we do it? We simply follow addition algorithm, and this algorithm is already present on your computer. And for performing this algorithm, the hardware also exists on your computer. So there are different circuits or different gates, or I could say different hardware is available to perform arithmetic operation. So by following addition algorithm, we can simply add 2 plus 1, and it happens over the binary of the number, right? So bit by bit we use this algorithm. Let's say 0 plus 1 is 0, 1 plus 0 is 0, 0 plus 0 is 0, and 0 plus 0 is 0. So we get 3, and this is our expected output. And how we do subtraction? We simply do subtraction over binary representation of a number. So if 0 minus 1 is 1, how? So how it is possible? Because we are borrowing 1 from the higher order bit. Higher order bit is 1, the next higher order bit. Okay, so this is how we perform the subtraction algorithm, and we get our result as 1, and that is correct. 2 minus 1 is 1 only. Correct? So far so clear. This is how we perform arithmetic operations like addition, subtraction, multiplication and division. So in case of positive numbers, everything is clear, everything is working fine. So far so clear. if we talk about the 4 bits number, then if I say how many numbers are possible if we have 4 bits, so I mean to say if we start our number by 000 till we reach all ones, so how many numbers are possible? So the possible numbers are 2 to the power 4 minus 1, that is equal to 15. So if we have 4 bits to represent any number, then there are 15 numbers are possible. So we can generate 15 numbers using 4 bits. Okay. So another way to count this is, let's say we have 4 bits, and here each bit is representing power of 2. So let's say first bit is representing 2 to the power 0, then 2 to the power 1, 2 to the power 2, 2 to the power 3. If we add all the powers, we get 15. Okay. So if I ask you about the range of numbers we can generate using 4 bits, it's going to be 0 to 15, right? Because this number is going to be 0 and then we increment one number each time, so we reach 15. Okay. So in C++ and C we have such type of database where we can only store the positive numbers, and we also call it unsigned integers, right? Because it is positive. So the advantage of using this type of data types is we get more number of numbers, right? Because in 4-bit we can store 15 numbers. But on the other hand, in Java there are no such type of database. There is no such type of data type available. The only data type available is integers, and this integers is capable of storing positive as well as negative number. So here we are not going to get a too large range, right? Because if we have 15, if we have a range of 0 to 15, in the 0 to 15 we have to store positive number also and negative number also. So obviously we are not going to store too much amount of number here, and we are also we also call it signed integers, right? Okay, so far so clear. So this is all about the positive numbers. Now the story begins when we include negative numbers in our number system. Okay. So let's consider now we also have to accommodate negative numbers also. So for example, we have 2 and -1. So how 2 is represented in binary? The binary representation of 2 is simple 0 0 1 0. But how we are going to represent -1 in binary system? So engineers came up with one idea. So what is that idea? So the idea is simple. Let's use the most significant bit to represent the sign of the number. So let's say if the most significant bit is 0, it means the number is positive. And if the most significant bit is negative, it means the number is negative. As simple as that. Now how we represent 2 is simple. It's simple. The most significant bit becomes 0 and else are same. Okay, remaining bits remain same. And what about -1? The most significant bit become 1 and the remaining bits remain as it is. Now here we have one disadvantage. Why? So here one bit is representing only sign of the number. So we are left with only 3 bits. Now we cannot store 15 numbers in this 3 bits. How many numbers we can store now? 2 to the power 3 minus 1 is equal to 7. So now we can only store 7 numbers here, and that is also including positive and negative numbers. Okay, so this is about negative numbers. So this is about representation of negative numbers. Now what about the arithmetic operation? Because if we have negative numbers, then obviously we have to perform operations on negative number also, right? So if we use our previous algorithm, addition algorithm and subtraction algorithm to perform same operation on negative number also, so it's not going to work now. Let's see it. If we have 2 and -1, if we want to add 2 and -1, we get 3, but we are expecting 1. So our addition algorithm fails here. In case of subtraction also, if we do subtraction also, we get wrong result. We are expecting 2 minus -1 is equal to 3, but we are getting 1. So our algorithm is not working here. After using this approach of setting the most significant bit as the sign bit. So this approach has 2 major problems. One problem is our arithmetic operation fails here and it is not going to work here at all. And the second major problem is we are getting 2 zeros, right? Just imagine that in mathematics we have 2 zeros, negative zeros and positive 0. How we are going to handle that scenario? So this same happens here also. So we have positive 0. It means if we fix the most significant bit to 0 and we make all the bit to 0, we get positive 0. And if we set the most significant bit to 1 and set all other bits as 0, then we get negative 0. And this is a major problem. It becomes really difficult to handle negative and positive zeros in programs. So obviously we are not going to use this approach. this approach is not going to work. So after thinking too much, the engineers came up with another idea, and that idea is, if you have negative numbers, just find the ones complement of that number. And what is meant by ones complement? We simply inverts all the ones bit to 0 and all the zeros bit to 1. So let's understand it. So let's understand this with an example. So let's say we have 2 and minus 1. So the binary representation of 2 is as same as before. But what about minus 1? So what we do, this bit is representing minus sign and the remaining bits are 0, 0, 1. So we find these 2's complement. So we are going to find the first complement of these bits. What we do, we simply have to invert the bits. So 0 becomes 1, 0 becomes 1 and 1 becomes 0. So we get 1, 1, 1, 0. Right? Now again talk about the arithmetic operation. What happens now? So if we do 2 plus 1, so this is the binary representation of 2 and this is the binary representation of 1. And if we do simple arithmetic operation, means if we do simple plus operation, we get 3. Okay, that is the correct answer. 2 plus 1 is equal to 3. Now let's say one number is positive and one number is negative. Then here we don't need any extra algorithm for subtraction. We simply use the addition algorithm to find the result. How? Let's see. This is the binary representation of 2 and for the negative numbers we have already calculated 1's complement and the value of 1's complement is 1, 1, 1, 0. Okay. Now we simply have to apply addition algorithm on this operation. So after applying algorithm, we get 0 plus 0, 0, 1 plus 1, 0, carry forward 1, 1 plus 1, 0, carry forward 1 and 1 plus 1, 0. We get 1 as extra bit. So what we do in this case, we simply move the 1 bit to the front and below least significant bit and we again perform the same addition. So 0 plus 1 equal to 1, 0, 0, 0, 0. So we get 1 as our answer and that is perfect answer because 2 minus 1 is equal to 1. So here we are getting one advantage that we do not have to use two algorithms for addition and subtraction. By using one algorithm only, we simply performing arithmetic operations. And in case of multiplication and division also, we only need one algorithm in case of if we find 1's complement. But this approach also has one problem, and that problem is again 2 zeros. Why? Even if we fix the most significant bit and set all the bit to 0, this will become positive 0. And if we set the most significant bit to 1 and we find the 1's complement of 1, then it becomes 1, 1, 1, 1, and this is nothing but a negative 0. Still we are facing same issues with 2 zeros. Now let's see how to solve this problem. Now after thinking again and again, the engineers came up with one efficient and the final approach, and that is to find the 2's complement of negative number. Let's see how it works. We know that after inverting 1's to 0 and 0's to 1, we get 1's complement, right? Till now we are okay. Now how to find 2's complement? So the binary representation of number 1 is 0, 0, 0, 1, right? So what we do? We simply do 1's complement. So this is the result of 1 complement, and then we simply add 1 to it to find the 2's complement. So after adding 1 to it, we get 1, 1, 1, 1. And this is the binary representation of the 2's complement of minus 1. Okay. Now talk about now let's move on to arithmetic operation, how it works. So if we add 2 plus 1, we get 3, and this is what happening in previous approach also. Okay. Now what about this approach? Now what about 2 minus 1? So here also it works perfectly. Okay, how? This is the binary representation of 2 and this is the 2's complement of minus 1. If we use the addition algorithm, 0 plus 1 becomes 1, 1 plus 1 becomes 0, carry 1, 1 plus 1 becomes 0 and carry 1, 1 plus 1 becomes 0, and this is our extra bit, right? So what happens in this approach, in 2's complement, we simply ignore this bit. In previous approach, in 1's complement, what we are doing, we were moving this bit to the least significant bit, below least significant bit, and we again performing addition. So we have to perform 2 times addition. So in this approach, we do not have to move this bit anywhere. We can simply ignore this bit and we get our answer, that is 1. So the advantage is, first we do not have to perform addition 2 times and we simply have to ignore this bit. Okay. So in case of, in this approach also our arithmetic operations are working fine. If I talk about multiplication and division, it's also going to work. You can check it out. Okay. But this approach has many advantages. let's see all the advantages one by one. So the first advantage is our 0 is gone. Yes, you heard it right. Our 0 is gone completely. How? Let me show you. So the binary representation of number 0 is 0, 0, 0, 0. And if I have minus 0, then if I convert and if I take 2's complement of minus 0, then again we get the positive 0 only. So here we have minus 0, right? So what is the 1's complement of minus 0? 1, 1, 1, 1, right? Because in 0 all are zeros, so we simply invert all the zeros to 1, 1, 1, 1, it becomes all 1's, right? And to find 2's complement, we simply do add 1 to it, right? We simply add 1 to it. So after adding 1 to it, it becomes 0, 0, 0, 0. And we get this extra bit because 1 plus 1 is 0, 1, 1 carry, 1 plus 1, 0, 1 carry, 1 plus 1, 0, 1 plus 1, 1 carry, and here it comes 0. So we simply ignore this bit in 2's complement. So we finally get our minus 0 is 0, 0, 0, and it is nothing but it is a positive 0, right? So this is how we avoiding 0 in 2's complement. So our problem is solved. Now 2 zeros are gone. Now next advantage we get using this approach is our sign bit is also preserved, right? So let's say in case of 2 we have 0, 0, 1, 0, it means the our MSB is 0 only. And in case of minus 2 also, if we find the 2's complement of minus 2, we get 1, 1, 1, 0, and the less and the most significant bit is 1. So we are getting this advantage that our sign bit is also preserved in this approach. Now third advantage is our arithmetic operations are also working. So if I talk about addition, subtraction, multiplication, division, all are working fine with this approach, and we have to only follow one algorithm only. We do not have to write multiple algorithms for performing multiple operations, okay? And second thing is we simply have to throw any extra bit. So in previous approach we have to carry forward that bit to the less significant bit, and then again we have to perform operations to get the result. But here we have to simply ignore the bit and throw away to get our result. So if I talk about programming languages, most of the programming languages use 2's complement to store negative numbers, okay? And the step to get the 2's complement is simple. First write the binary representation of a number, then invert all the 1's to zeros and zeros to 1, and finally add 1 to it. So we get our 2's complement. So what is the 2's complement of minus 2? It is 2 to the power 1 plus 2 to the power 2 plus 2 to the power 3, and that is 14. So the binary representation of 2's complement of minus 2 is 14. So there is also a direct way to find 2's complement, and that is 2 to the power n minus x, where n is the number of bits. And here we are talking about only 4 bits, so that's why 2 to the power 4 minus 2, it becomes 16 minus 2 and 14. So this is the direct way to find the 2's complement of any number. So far so clear. Now let's talk about the range of the number. So let's say if we have positive numbers as well as negative numbers. So obviously we are going to have lesser number than only positive number, right? So the range of these numbers are going to be minus 2 to the power n minus 1 to 2 to the power n minus 1 minus 1. Why I am doing n minus 1 here? Because one bit is used just to represent the sign. So that is why we have only 3 bits now, and total number of bits are 4. So now we have only 3 bits. So if we calculate this, we get minus 2 to the power 4 minus 1 to 2 to the power 4 minus 1 minus 1. So we get minus 8 to minus 8 to positive 7. It means there are 8 negative numbers we can store in this range. 1 is our 0 and 7 are positive numbers. Okay. So if we total 8 plus 0 plus 7, it comes out to be 15. So total number of numbers we can store in 4 bits are 15. Out of 15, 8 are negative number, 0 is one number, and 7 are positive numbers. Correct? So if I talk about Java, so Java uses 32 bits to store integer values, and the range of that integer is going to be minus 2 to the power 32 minus 1 to 2 to the power 32 minus 1 minus 1. It becomes minus 2 to the power 31 to 2 to the power 31 minus 1. So this is a huge range. Okay, so there are so many numbers you can store within this range. But it would be great if we have data types like to store only positive numbers. Then in this range we can store so many positive numbers. But currently as we have negative numbers also, so we cannot store so many numbers. We have to divide our range between two parts, one for negative and one for positive. So now let's have a quick recap of what we have learned so far. So we have discussed about numbers, and numbers are the fundamental units of data. And then we have discussed about positive numbers and what are the range of positive numbers. So how many numbers are possible if we have 4 bits. Then we have discussed about negative numbers, and we saw that if we consider negative numbers, then we may face problems, and problems are 2 zeros, negative and positive, and we are not able to perform arithmetic operations. And we saw 3 approaches to solve the problem. One is using the signed bit, second is finding the ones complement of a number, negative number, and third one is the finding the twos complement of a negative number. Okay, and the third approach is efficient and working fine in all the cases. Then we saw that how to find the range of numbers. So let's say if we have 4 bits, then how many numbers we can store in these 4 bits, including positive numbers and negative numbers. So I hope now you have a good understanding about how numbers are represented in binary format and how numbers are stored in memory in binary representation. So this is it for this video. Thanks for watching. See you in the next video.